Welcome to All Things Policy, a daily podcast by the Takshashila Institution. We are a bunch of policy nerds based in Bengaluru, and we like bringing fresh perspectives to Indian affairs and Indian perspectives to global affairs. So grab a cup of coffee, sit back, and join us for today's chat.
Hello, folks. Welcome to another episode of All Things Policy. Satya and I today are going to discuss about AI hardware and why it is relevant for policymakers and how it impacts the India AI mission that was recently announced. Satya and I are both research analysts with the High-Tech Geopolitics program at the Takshashila Institution. Welcome, Satya. How are you doing today?
Yeah, doing better. The weather is better at Bangalore this week, thankfully. And yeah, as you mentioned, AI hardware has become the subject of a lot of policies, be it in foreign policy, be it in domestic, economic, and industrial policy. It's something that's at the center of a lot of critical infrastructure, mainly because AI hardware isn't exactly just hardware that is only meant for AI workloads. It's also a huge component of high performance computing infrastructure that goes into your supercomputers, that goes into maintaining our cybersecurity grids, that goes into maintaining the global digital presence of a lot of companies online, right? So that's the primer, I guess.
Yeah, AI has become widespread in the recent era, right? We are hearing AI being introduced into all sectors of the economy, all technological fields. Even governments have taken interest, and India is no exclusion. India is also exception. India has also set up the India AI mission. And just to highlight why the hardware component is so important, half of this budget, half of this 10,000 crore budget has been earmarked for buying GPUs to deploy an India compute for AI. So this is a topic worth discussing. And to give our listeners a bit of context, why don't we start with the broad overview of where hardware started and how it has gotten specialized into AI hardware architectures today. Why don't you give us a quick?
Right. So before we do that, the thing we don't understand for everyone is AI generally exists as a supply chain, right? So the components of the AI supply chain would be your data and computation, which are the foundational, like the stages, the layers of the chain upon which you have models, you have applications, and finally you have consumption of whatever, AI, machine learning, whatever we talk about it, right? So alongside data, compute power is the other foundational stage, right? Which means compute hardware, AI hardware can come into play at every single part of the supply chain. It is used for manipulating the data that comes in, right? To label them, to analyze them, etc., to make it easier for the models to understand. Then it's used to train the models themselves. So, and there are models which can range in sizes from OpenAI's ChatGPT, as large as those, to something as small as a computer vision model that can run off your laptop, right? And then finally, people who are developing applications on the top of these models or by calling APIs from these models, they need to fine tune a particular model for their usage, and for that also you need compute. And finally, consumption, like MacBooks or on your the newest iPhone that was announced yesterday, the iPhone 16, they have an entire part of their the chip, the SoC, the system on chip, dedicated to running AI tasks only. So when you, for instance, take a photo and you can erase the background or an element in the background of the photo to make it look better, and that's an AI related task. That is happening because of the specific part of the chip that is meant to do to conduct AI workloads. So across all the stages, you have AI hardware come into play. So usually until I think the early mid 2000s, the manner in which compute interacted with AI or machine learning, neural computing workloads was primarily bottlenecked by the way that it's so difficult to program for those specific hardware, those specific chips, the things that connect multiple chips together, etc. But I think since the early 2010s, it's accelerated quite a bit, and we can divide AI hardware generally into three different components. First is the accelerators or processing units themselves. So that includes your usual CPUs, your GPUs, and there are multiple, like, very specific kinds of chips as well, like Google's tensor processing units, which are only and only manufactured, fabricated to be used for specific AI workloads. Then you have FPGAs as well. So those are the logic. Those are the units of AI hardware that actually do the number crunching, the multiplication, the algorithmic part of crunching the AI workloads. Then you have memory subsystems. Those are the ones that are relevant because the amount of data that is needed to, for instance, train a particular model is huge. And this also needs to be done at a very fast rate because, for instance, if you ask a query of ChatGPT and ChatGPT takes, 10 seconds to respond to you instead of 2 or 3 seconds, that's a huge problem, right? That's a problem for industry as well as for the end consumer. That's why. So this kind of data transfer between the memory and the processor needs to be very quick as well. So bandwidth and latency is also very important there. So memory and storage systems are also very important. So that includes your dynamic RAMs, which is that's used in a consumer device as well, like smartphones and PCs, as well as something called HBM, which is high bandwidth memory. It's a very advanced type of memory module that is much more expensive and is usually integrated onto the logic processor itself, right? It's very close to the logic processor, so it requires a lot more finesse in terms of the fabrication and packaging technologies. And and then finally we have something called networking and interconnect capabilities. This is important because usually what happens is you need to be able to connect different parts of the same chip together to be able to conduct or work on these workloads better. At the same time, you also need to be able to connect multiple chips, this accelerators together as well, to parallelize the workload crunching. For instance, you can, let's say, divide one workload into 4 smaller workloads and then let 4 different GPUs very quickly be able to process that and then throw out an output, right? So this needs to be done in a systematic way so that there aren't, what do you call it, any sync up problems essentially between those. Then you also need to be able to connect data centers where clusters of these chips, etc., are also situated, right? So you need to be able to make sure people who are consuming this service, AI as a service, etc., are able to access, are connected to the data centers themselves and data centers among themselves as well. So that requires a very specific kinds of networking and interconnect technologies as well. So so I'll stop here and we can proceed from there.
Okay, so this brand of compute that has emerged for AI in specific, it has emerged from a basis of general process computing that has finally specialized into what we have today, right? So how does that chain look like? Where did it start off and where are we heading?
As in talking about how essentially what consumer grade hardware used to be and why it has now become so specialized for AI,
for
right?
instance, you were talking about the recent iPhone that has an NPU that can run AI model locally to do a lot of what they call Apple intelligence. And a few iterations before, we probably didn't have an NPU in the iPhone, and the CPU was the dominant processor that people considered when they were considering buying the iPhone. And now suddenly there is an all new element to this processing capability, which is this what they call the NPU. And this trend is pervasive across a lot of other technological sectors also. And this can be attributed to the rise of AI, right? Would you tell us a little bit about that?
Yeah. So first of all, the use cases for computing hardware were generally very scattered. And the problem there was people who wanted to program for, let's say, something that was very specific in its ambit, like machine learning or like only crunching huge data sets of numbers across spreadsheet, etc., right, for financial sectors. the people who are programming for those would not know how to program for a particular processor or processing unit that is required for rendering graphics in a video game. So because of all of this, whatever general purpose computing hardware is used across all the sectors, they were generally inefficient, and developers across sectors weren't exactly transplantable, substitutable, right? So I would say the first major revolution that happened in this area was Nvidia. So Nvidia is, everyone knows who they are now, but back in 2006 they were very specifically a gaming graphics processing unit designer. So what they did, they faced a problem of being able to program for games easily. It was a very difficult thing to do back in those days, because graphics cards also had a lot of specific units in the chip itself that required very specific knowledge from the developer's part to know and code for that. So Nvidia did one thing, which is they streamlined all of these functions into a single programmable unit, which they now call a CUDA core. And then they built on top of that, very, very tightly integrated, a software development platform called CUDA. But in this case, the platform used was very easily familiar to developers across all sectors, because they used very common languages like C, C++, and Fortran. So what this meant was that, hey, you solved the problem of talent, right? So talent which knew how to program for a particular NVIDIA GPU can now do so for a completely different sector using the same GPU as well. So a common platform, both in terms of software and hardware, made the idea of general purpose computing hardware, which is very relevant when it comes to scientific computing as well. So when that ended up happening, the trend began to grow such that scientific computing, which had a very specific kind of requirement, which required large memory, it required things to be run for days on end. So consumer specific hardware also then began to be catered to those. So now NVIDIA, for instance, uses CUDA cores across both the gaming GPUs, but they've also created the enterprise or the high performance computing, or what we now call as AI specific GPUs, only for scientific computing and AI workloads, right? So while they still use the same CUDA cores alongside some other specialized cores like tensor cores, which also find presence in their gaming GPUs as well. But this AI specific GPUs, for instance, do not have a display output at all. So you can't use them to play games. They don't support the kind of instructions that are required for, that the gaming GPU counterparts do. And vice versa. The gaming GPUs, for instance, do not support the kind of instruction formats that the AI specific GPUs do. However, if anyone wants to program for an AI application using either of those GPUs, they can still continue to do so, and their application will run on both of them. Just that it will be slower on the gaming GPU as compared to the AI specific one. So if we take this trend and look at how it has happened in other side of consumer hardware, like which is CPUs and on your phones, right? Whenever Qualcomm, for instance, made its Snapdragon chips, right? So that the flagship chips that go into your smartphones, I think until 2015, they did not have a part of it dedicated to an NPU for running machine learning or neural workloads. But in 2015, I think with the Snapdragon 820, they did so, because the things that required, computational photography, for instance, right? I mean, your phone camera is completely based on computational photography. In order to, account for the limitations of physics, because your phone is so small and your lens is so small, you need to be able to understand algorithmically how a particular scene should look like and compensate for the limits of physics that you need to contend with. So computational photography began rising around that time, and therefore you needed a particular area of the chip alongside something called a digital signal processor. That's not relevant right now, but because workloads like this began rising on the consumer side of things as well, you needed to be able to do this in a more efficient way, in a more bespoke way, right? So that's why you begin seeing what Apple is now calling its Apple Intelligence, taking advantage of hardware specific attributes. So consumer level hardware also now has started being optimized for AI and machine learning workloads as well. But however, we need to keep in mind that consumer hardware isn't exactly very substitutable for AI specific hardware, although I would say 70 to 80% of the times They can be. They won't be efficient. It has a huge bearing on time to market for a lot of developers, simply because they'll be slower. They may not be as reliable in terms of precision. And that's exactly what China has been doing, for instance, right? Since 2022 October and 2023 October, when the US export controls targeting, advanced AI chips hit China, essentially they've been trying to use Nvidia's other, high-end gaming GPUs to try and, substitute the same kind of workloads that Nvidia's H100 GPUs used to do. And then, the export controls expanded, even, incorporating in its ambit the highest end Nvidia gaming GPU called the RTX 4090 in it. So now I think they have gone down a rung and gone to the RTX 4080 as a possible, substitute. But again, so it's a huge handicap for when you think about building AI infrastructure at scale. You can't do that with consumer level hardware. It's slower. The people developing for it, the industry that's reliant on it, will encounter a lot of problems doing it, which is why the export controls are such a huge deal. But if you think about in like smaller scale, like a particular developer trying to train a model on his own laptop or something, things like this are perfectly fine for now, and very much dependent on the size of the model or the kind of workload that an application is running on. So yeah, so depending on a use case, you can sometimes substitute consumer level hardware with AI specific hardware.
Okay, so besides the trade restrictions that you touched upon, what are the other policy implications of the AI hardware market? For instance, is Nvidia's overwhelming monopoly a case of market concentration, and do you see that causing problems for the industry down the line and for India's interests as well?
It's a good question. That's got multiple dimensions here. First of all, as a general principle in both, competition, I mean, in terms of economics, the moment you have market concentration for such a strategic technology, and it's not just AI, right? It's NVIDIA's GPUs are used across multiple domains, and they are the mainstay there, which means that the moment you have any sort of dependency like this, the potential for it to become a vulnerability also grows. So if, for instance, whatever reason, NVIDIA's production runs stop, or let's say TSMC, which is fabricating NVIDIA's GPU's logic chips, that's disrupted somehow. Or if in Korea, SK Hynix and Samsung, the ones who make the memory for NVIDIA's GPUs, aren't able to do so properly, what happens to the data center infrastructure globally? Because the moment you have any sort of single point of failure, it's very difficult to address that. Now, the obvious answer would be people would say, oh, why not just substitute NVIDIA's GPUs with Intel and AMD alternatives? The problem with that is NVIDIA's dominance isn't just the hardware that's the GPU itself. As we mentioned, there's a CUDA, which is NVIDIA's both chip design architecture as well as the software platform. The software side of things is the primary reason why NVIDIA has become so dominant, right? So it's easy to program. You now have network effects because you have students and developers who in their academic research periods have become familiar with NVIDIA's GPUs and how to program for them. And the industry also wants developers who know how to program for the number of GPUs that already exist in their infrastructure. So you now have this kind of network effects erecting a lot of entry barriers for GPUs from other vendors like Intel and AMD. The other thing is NVIDIA. There are a lot of ways to create alternatives to CUDA, either through a competing ecosystem like AMD has with something called Radeon Open Compute. And the problem with that is it's not as mature. There's a lot of teething problems that needs to overcome. The other problem is there's a way to, let's say, convert CUDA-based applications into source code can then be used to create the same application that can run on AMD GPUs, right? And similarly with Intel as well. While it is comparatively easy, but it still requires developer time to be devoted to this. The other way in which you can create an alternative to CUDA is essentially creating a translation layer, which is a software that will interface with an application and a non-NVIDIA GPU and basically make the application think that it is running on an NVIDIA GPU. And then, it translates the application's code, etc., to be in real time essentially, and to be able to run on a competing vendor's offering, right? The problem now is, I think, the most prominent example of this was called ZLUDA, ZLUDA, and AMD had been funding it until recently, but it stopped, and the project is in limbo right now, primarily because NVIDIA has begun reiterating its licensing terms for CUDA. And because CUDA is free to use, NVIDIA's licensing terms basically say that, hey, if you're going to use CUDA, you cannot use this to reverse engineer it and create translation layers for CUDA, right? And while the legality of it hasn't been tested in courts yet, it's a huge barrier right now. So what's ended up happening is that the development of translation layers is one way in which we can feasibly make sure there are alternatives to NVIDIA in the GPU space. But there hasn't been a concerted effort on the part of nation states or companies and organizations really to see this through. As of now, whatever, I think there's another project called Scale, which is ramping up to do this exact same thing, but I don't think it's open source. But yeah, imagine if for a nation state, you can create legal mandate as well as maybe initiatives that can create translation layers. So just for the sake of strategic autonomy and independence, so resilience. If you have something like that, you can foster competition across applications across the other, let's say, homegrown alternatives to GPUs, right? You can use the same software programming model and build on top of that. So that's a huge opportunity there, especially if you have concerns about vendor lock-in. There's a lot more to it, but I'll stop here for now.
Satya, besides that specific recommendation of nation states possibly mandating that the transaction layers be allowed and to foster competition and to prevent market concentration, are there any other recommendations specific to India, especially given the strategic importance of AI as a technology and the necessity of the healthy AI ecosystem in the country? Do you have any other recommendations that the Indian government can possibly consider?
I mean, there are many, but first of all, we need to rethink what exactly we want our compute infrastructure to be. Yeah, sovereign compute infrastructure is good to have because we need that for resiliency purposes. But if the idea is also to be able to use that compute infrastructure and provide it to developers, to academia, everywhere, etc., then first of all, 10,000 GPUs, for instance, the India AI mission are peanuts. It's not quite enough. And the resulting infrastructure that you need to build on top of it, the data centers, as I mentioned, the interconnect and networking technologies that is needed to connect these data centers and to everywhere else in the country. Then you have a huge talent shortage that's really needed for data centers as well. On top of that, are GPUs really the best hardware alternative to go for, depending on the use case? And this is where a strategic direction in terms of what kind of AI models are we looking to build, as a nation state? Are we trying to build a sovereign AI? Are we trying to build a foundational model, a large language model to rival, let's say, ChatGPT? Or do we want very specifically smaller AI models that cater to very specific, use cases, right? So, and this is what we hear a lot in the news right now, that India is the AI use case capital in the world, is that we have very specific use cases that, like, in agriculture or in healthcare or in finances, that can be accelerated or refined through AI, right? And for that, you don't necessarily need, tens of thousands of GPUs. You can have smaller clusters of compute. You can have disparate sources of compute. You can have more efficient sources of compute, right? Like we can have less power hungry, more efficient chips that are only meant for AI workloads. And you have a lot of suppliers, designers in the Indian market and abroad who are making chips only for these workloads, right? So we don't necessarily need to train something at the scale of ChatGPT, or we can train much smaller models, and you can deploy them in much more power efficient AI compute infrastructure. Because remember, India is also starved of power and water generally, and data centers require quite a bit of those. So the trade-offs that we're making here is something that policymakers need to keep in mind. And also the fact that even if we do end up going with 10,000 GPUs, you need to remember that at the end of the day, you're going to be dependent on NVIDIA for everything. Like let's say like a few hundred GPUs need to be repaired. You're going to be tied to NVIDIA for those services. For instance, buying NVIDIA GPUs also means you need to buy the downstream networking and connectivity solutions as well, which is again completely owned by NVIDIA. For instance, like NVIDIA's networking solutions revenue has also gone up to 10 point something $billion, simply on the back of the fact that it has a monopoly essentially in the GPU market, right? So all of these concerns are something that policymakers need to keep track of.
Well, thank you, Satya. That was a great overview of what the AI hardware sector looks like around the globe. I hope our listeners enjoyed this episode of All Things Policy. We want to continue doing episodes having with conversations related to AI and hardware. So stay tuned for that. Thank you, folks. Have a good day.
If you liked our show, dive into Takshashila's research on technology, strategy, and economic affairs. Check us out at our Twitter handle at Takshashila INST or our website takshashila.org.in.